Can you see my screen?
Yes.
Okay. Good morning, everyone. I'm Irene Pessolano, a PhD researcher with Professor Raffaella at the Mechanical Department in Politecnico di Torino. I'm glad to explain you our work on innovative processing for ceramic ball manufacturing. This study was performed on a new abrasive material, and we use an analytical, experimental, and numerical approach. Okay, before going into the detail of our study, let's introduce our framework. We deal with ceramic balls for hybrid bearings. In this frame, the ceramic balls are used thanks to their physical, thermal, and electrical properties to guarantee an high-performance product and safety in their application. In fact, compared to standard bearings with steel balls, they have a higher wear resistance thanks to the higher Young modulus, a larger temperature range due to the higher coefficient of thermal expansion. Ceramics guarantee self-lubrication properties and does not allow the current flow through bearings, obtaining an electric insulation effect. Those are only some properties of ceramic balls that explain why ceramic balls are used in hybrid bearings and why hybrid bearings are implemented in several fields. The major goal of this research is the development of ceramic balls production. In fact, in general, the technological progress in hybrid bearings develop high wear and abrasion-resistant materials for rolling elements. The manufacturing process of bearing balls presents new challenge, and it requires time-consuming and costly process. In this frame, the bearing manufacturing industry is demanding improvement in grinding wheel geometry, in the input process parameter, and on materials. This work aims to investigate new abrasive coating for grinding wheels for ceramic balls production, for silicon nitride ball production. Therefore, to compare a traditional electrodeposed diamond versus a diamond-reinforced metal matrix coating, in order to investigate the wear resistance and the final surface characteristics of silicon nitride balls. As a first step, we perform an experimental characterization before performing the wear test. Then the experimental setup for the wear measurement parameters. After the experimental approach, we perform a finite element analysis and the wear simulation procedure. The last step is used to simulate the manufacturing process. The experimental investigation involved the use of silicon nitride ceramic balls with a nominal diameter of 6 mm and 2 different diamond coatings employed in pin-on-disc test. A diamond-reinforced metal matrix, indicated as DMMC, and a synthetic diamond coating with a maximum particle size of 30 micrometer, indicated as D30. Sample preparation was carried out in collaboration with Politecnico, Tsubaki Nakashima Internal Application Laboratory, and the Research Center at the Trinity College. A set of 6 nominally identically silicon nitride bearing balls was employed for the investigation and was retrieved from the production line at Tsubaki Nakashima. The quality and the uniformity were preliminarily assessed by visual inspection with the purpose of avoiding elements characterized by surface imperfection or defects. Mechanical properties of the material are reported in the table in terms of their average Young modulus Poisson ratio as recorded from 3 independent measurements. Coated discs were subjected to preliminary evaluation by means of the scanning electron microscope, and the outcomes are displayed in the figure in the front view and in the cross-section view. Subsequent image analysis showed that in case of DMMC, the employed deposition process led to a partial crushing of the diamond particles, which their final dimension being comprised in 50-75 millimicron range. By comparison, the D30 coating was found to be slightly coarser, with particle dimension comprised between 50 and 120 micrometers. Abrasion and friction measurement were carried out on pin-on-desk configuration by making use of the disc and bearings prepared as said before. Tests were performed by an Anton-Par TRB turbometer. The functional scheme and equipment that is compliant with the ASTM G99 and ASTM G130 standards is shown in the figure. As a result of preliminary work, it was concluded that for each combination of bearing ball, that is the pin, and coated substrate, the plate, two wear measurements were performed by imposing the pin plate contact at 7 and 11 millimeters from the disc center, and by adopting different value of relative rotating speed between 20 and 40 RPM. Normal load and sliding distance were fixed at 1 Newton and 150 meter respectively. Testing conditions adapted for the performed test are synthesized in the table, and as you can see, what differs from each test is the local linear speed. For each pin-on-disc test, wear of contact body was calculated by appropriate linear dimension, length or shape change of the pin, and depth or shape change of the disc track. Subsequently, wear linear measurements were converted in wear volume through appropriate geometric relation reported in the two standards G99 and ISO 18535. A further parameter quantifying wear is introduced by the Archard equation. This approach is adopted to model the friction phenomenon for the purpose of determining the wear coefficient K, a dimensional, and the wear rate U expressed as micrometer per hour. Once the volume of the wear product, the sliding length, the normal force between the surface hardness are known, the wear coefficient can be calculated thanks to the Archard equation. And the wear equation can be also expressed as the wear rate. As expected, values of sphere volume losses calculated with both standards were very similar. However, values of the disc volume loss calculated with the standard were found to be positive, thereby indicating a disc volume increment rather than a decrement. Such an output can be explained by referring to the significant roughness of the disc and the deposition of the brights in the surface irregularities, with the resulting conclusion that the formula proposed for the calculation of volume loss may not be reliable for disc in this kind of experiment, where the abraded part is the ball, is the pin. These results is confirmed by profile measurement and by visual and optical microscope observation of the wear track on the disc. When considering the entire set of experimental data obtained from tests carried out with the MMC, it can be observed that the volume loss were found to increase with values of local linear speed decrease. In particular, this can be assessed by progressively considering the results of test 1 and test 2 carried out by using the same DMMC specimen with a linear speed of 29 and 23 millimeters second respectively. And test 3 ran with a second coated disc DMMC specimen 2 with a linear speed of 40 millimeters second. Results obtained with test 4 with an highest linear speed equal to 34.5 millimeters second seems to deviate from the identified trend, with a volume loss that was found to be higher than expected. However, this can be explained by considering the higher surface roughness of the DMMC specimen 2, which, as proven by experimental observation, can counterbalance the effect of increasing the contact speed. For D30 and DMC specimen 2, higher linear local speed results seem to be related to a higher abraded volume for both coatings. For the analysis of the delta volume, the two different volume loss estimation proposed in the two standard gave results with a difference lower than 8%. As reported, this difference does not affect the discussion of results, and both formulations can be applied to comparing the wearing performance of the investigated coating. Then, through the values of volume lost by the balls, according to the ASTM G99, the wear coefficient K and the wear rate of the 6 tests were calculated using the Harshard equation. Figures in the slide show the wear coefficient and the wear rates of the silicon nitride balls using during the test. It is evident that the D30 coating, which has a higher surface roughness value than the DMMC, performs a strong adhesive action on the balls. In figure, it can be observed that the wear coefficient K increases with the increasing sliding linear speed. In fact, according to the model, all the parameters are constant for different testing conditions, and the variable is the abraded volume, which increases with increasing local linear speed. After the experiment, we performed a finite element analysis on ANSYS software. First, a static contact simulation was performed to find the reaction force needed for the second simulation, the pin on disc one. For what concerned the wear modeling procedure, the continuous process was discretized into several steps. Therefore, the contact pressure between the contact surface was calculated. Then the wear increment and the contact nodes of every element were updated. At the end, the total wear depth calculation on the contact surface was possible. The model assumed that during each step contact, the parameters are constant, as pressure or material homogeneity. Then a simplified and a linear model was developed, and we focus on the time step and the mesh evaluation. In fact, good time step value is given by the trade-off between precision and calculation time. Moreover, a two-course mesh can lead to a worsening of the results. In this slide, we have the comparison between the experimental and numerical results. The percentage difference of wear depth between the pin on disc test and the ANSYS simulation is always lower than 8%, unless for the test 1, where the computational time is low, is less than 1 hour. The experimental and simulated wear rate over time is reported in this slide. What we can see is that the trend is very similar, therefore the adopted procedure works also in the case where the material is not homogeneous, like in our coatings. In conclusion, we can say that the experimental procedure for the wear behavior of diamond abrasive coating match the analytical models in the wear estimation standards. Pin on disc tests allowed to point out the wear parameter between non-homogeneous materials. Then the mesh optimization of wear pin on disc simulation was pointed out thanks to the nonlinear static testing simulation of earth-end contact. Last, the wear simulation procedure will be applied for simulating the entire grinding wheel processing procedure. That's all from our side. I thank you for your attention, and we are available for any question.